alıyoruz. Başlayalım kayda. Now it's the time to begin. Professor Dr. Ekrem SAVAS,
Yes.
who is director of Uşak University, accepted to give a plenary talk to us. Although he is very busy with administrational duties. Thank you very much, Ekrem SAVAS, Professor Ekrem SAVAS. Here you are.
Okay, thank you so much. First of all, I would like the organization committee and especially to you for inviting me to share the papers with the colleagues. And I wish everyone a good night. And today, the title of my talk, A New Double Sequence Spaces Defined by all its functions. So I will mention the double sequence spaces and also have the credit to some sequence spaces by all its functions. So I will give some brief introductions before giving the main main results. Actually, the first, I will mention the statistical convergence. Statistical convergence was introduced by the FAST, and the same time in the Bentley also, the Schoenberg also defined the statistical convergence. Statistical convergence, if n denotes the set of the natural numbers and the k subset of the n, then Kmn denotes the cardinality of the set, K and the intersections of Mn. And so we define the upper and the lower natural density of the subset K as follows. And this is the upper the density we define like this way. Limit is going to the infinitive, the limited exists, and the lower densities defined like this way, then the limit is exists. If the upper and the lower natural density is equal, we say that this natural density of K is exists, and usually we are using this symbol to denote that dk, and clearly dk equal to this limited is exists here. So we can give the definition of the statistical convergence. Sequences xk natural numbers is said to be statistical convergence to the number L if for epsilon greater than 0, this k epsilon, this set has the natural density 0. Actually, we know that every convergence sequences is the statistical convergence, but usually the converse is not the true. After definition of this and some works, for example, the Friedman and Salat and the Connell papers, these are supposed to be very famous to apply some other subject. Looks like the algorithmic theory or fuzzy and number theory, or also the probability theory. We can get the chance to apply the statistical convergence step. Three papers, the very main papers to understand what is going on about the statistical convergence. And 3Ds defined actually they show that the concepts of statistical convergence sequences and the statistical quotient sequences are shown to be the equivalent. Also, statistical convergence is studied as a regular summability method. It's shown that it cannot be included by any matrix. Any matrix method. There are two Tauberian theorems proved in that papers. One is use the Tauberian condition, which is shown to be best possible, and the other is the concern with the gap sequences and further prove the following theorems. These theorems, the statement of the theorems, the following statements are equivalent. First, X is statistical convergence sequences, and the second one is X is the statistical quotient sequences, and third one, X is the sequence of which there is a convergence sequence Y such that xk equal to yk almost everywhere k. So, and the next theorem, no matrix summability method can be included the method of the statistical convergence. It's a very important theorem. And the third one, if x the sequence is such that statistical limit xk equal to y, L, and also delta xk equal to the 1 over the k, then limit this sequence is the convergence and equal to the L. Later on, this another paper is the base paper for the statistical convergence, which was published by the Salat. He presented that the set of all bounded statistical convergence sequence of real numbers is a nowhere dense subset of the linear norm spaces L infinitive. And infinitive is a set of the all bounded sequence of real numbers, and the set of the all statistical convergence sequences of real numbers is a dense subset of the first Bayer category in the Fresnel spaces S. Throughout the paper, we noticed that by M0, the set of the all bounded statistical convergence sequences of the real numbers. So he proved two theorems, actually the three theorems, but first theorem is the set M0 is the closed linear subspace of the linear norm spaces L infinitive. And the next one, the set of M0 is a nowhere dense set in L infinitive. denoted by S0, the set of the statistical convergence sequence of real numbers in what follows as denotes the pressure metric spaces of all real sequences with the metric. So he proved the next theorem. The set, the first condition of I, the set S0 is the dense in the spaces S, and the next one, the set S0 is the set of the first bare category in the space S. Many years ago, about 20 years, more than 20 years ago, then the Mursalan defined the lambda statistical convergence as a generalization of the one kind of the statistical convergence with that papers. That papers is published Mark Slovaka 2000, and in that paper he proved some inclusion theorems as follows. And here lambda in the big lambda, then xk is the convergence to L about under this sequence spaces. This implies that xk is the convergence, lambda statistical convergence, and inclusion is the proper. And the next condition, if x is the bounded and also statistical convergence to L, then xk is the convergence to L under under the sequence spaces. And hence, so xk is the convergence to L under the C0, means provided that xk is not eventually the constant. And the third conditions, this is the bounded and this lambda statistical convergence sequence equal to this the Dole Poisson and also the bounded, then this is equal L infinity here. So we know that this is a set of the bounded sequences. And the next one, he got another inclusion theorem. Statistical convergence is subset of the lambda statistical convergence set if and only if this limit is x and greater than 0. He proved the two conditions is very important. And recently, the mathematicians extended the statistical convergence by using the order of alpha, and we mentioned this one in the references 2 and 4, and they replacing the n in the definition of statistical convergence. There was the 1 over the n. They replacing the n by the n alpha in the denominator in the definition of statistical convergence. So it was observed into that the behavior of this new convergence was not exactly parallel to that of statistical convergence, and some basic properties were obtained. Very recently, the notions of lambda double statistical convergence of order alpha and was studied in the references 6, and also some other papers you can find references to 5. Throughout this paper, we will use these functions weighted g from the R plus times R plus to the R plus, and where g x and m is goes to infinity for any sequences x and m in this part, with the is going to the infinity. And just I will mention what is the double sequence spaces, and who has defined the first time I will mention this one. This convergence of the double sequences was given by the Prince-Scheim as follows, and there is this double sequences. This sequences has a Prince-Scheim limit L, denoted by usually P limit x equal to L. So that provided that given epsilon greater than 0, that exists and belongs to the set of the natural numbers, such that this is the less than epsilon. whenever KL is greater than or equal to the N. We shall describe such X more briefly as a P-convergent, and in the later stage, double sequences were introduced and studied by the Peterson and many others. We use the symbol C2 to denote the class of the P-convergent sequences. A double sequences xk is bounded if this norm equal to this one, and let L2 infinitive and C2 infinitive be the set of the real or complex bounded double sequences and the set of the bounded and the convergent sequences. So the basic question here, the extent of the generalized limit has been settled in the variety of the ways. The standard proofs appear in the references 1. This proof, based upon the Banach theorem, actually leads to all generalized limits, and this fact was used in the references 14 to obtain the properties of L. And also references 11 here extended double sequences certainly results obtained by the Rollins for simple sequences, and now we will give you the definition of the Banach limit as follows. A linear functional L on here is said to be the Banach limit if it has the following properties. First one is double sequences should be the positive for positive the sequences, and the second one L equal to the 1. This is the EK actually EKL. This is the 1, and the third one there is the shift operator here. Lx equal to L S1 S1 S10x, and another one L S01x, and the third one L S11x. S is the shift operator, S01x, S001x, and S11x actually define here. You can see, and the first one S10x actually xk plus L as the first term is shifted, and the next one x the second term is shifted, and the third term is the both xk plus 1 and the L plus 1 is shifted here. Usually we are using the B2, the set of the all Banach limits on L2 infinitive, and a double sequences xkl is the said to be almost converges to the number L if all the limits to the coincide for all Banach limits. By using this definition, Morris and Rose defined the almost convergent double sequences as follows. KL is said to be almost convergent to the number L if this limit exists and equal to the 1. Here, the average of value of this sequence is taken over any rectangle, like this way, and this is going to do L if P and Q goes to the infinitive, and this convergence is the uniform in M and also N. We denote the space of almost convergent double sequences by C2 head as follows. This is this limited axis and equal to the 0 uniformly in P and Q, and here T, K, L, P, Q, 1 over the K plus 1, L plus 1, Q equal to P to the up to the K plus P, and the next summation is the L equal to the Q, L plus to the Q. So another definition, a double sequence is strongly double almost convergence to the number L if this limited axis and equal to the 0 uniform in P and the Q. So also here, also we are using this C hat, C2 hat, this one, to denote the space of strongly almost convergent double sequences. It is easy to that those inclusion is the hold. Later on, Mursalen try to extend the statistical convergence to the double by using double sequences as follows. There is the real double sequences XKL is said to be statistical convergence to L. This is the double sequences, provided that for each epsilon greater than 0, this limited exists and equal to 0. We usually statistical convergent, if the X is statistical convergent, then X not to be the convergent, and also it is not necessarily bounded. About the double sequences for the statistical convergence, there are some papers you can apply that. The references 12, 3, 20, and 32. Then so you can apply this to all the references. Now there is another definition: lambda equal to the lambda n and the mu equal to the mu m to non-decreasing sequences of the positive real numbers, both of tends to the infinitive as n and m approach the infinitive respectively. And also lambda n plus 1 less than of the lambda n plus 1 and the lambda 1 equal to 1, and the same thing for mu m plus 1 less than or equal to the mu m plus 1 and the mu 1 equal to the 1. We write the generalized double Dole Poisson mean by with this expressions here, and a double sequence is said to be double the Dole Poisson summable to the number L if this limit is exists and equal to the L when nm is going to the infinitive in the Prisheim sense. And also throughout this paper, we shall use this symbol by lambda n mu m, and also we will use instead of we will use this one instead of this term. And already I mentioned the G and the big capital G. We will denote the class of all such a function from here, the G here, and such a function set. So now we will define, also throughout the paper, I will use the XKLPQ instead of this one. So when you see this symbol, you will understand that this symbol. So I can give now the definition. Lambda is the sequence of the lambda and lambda nm of real numbers defined as above, and let G belongs to the G. A double sequence is said to be lambda double almost statistical convergence to weighted G if there is a complex number as such that this limit is x equal to the 0 uniform in P and the Q. And that case, we are writing this one. In this case, we will use this symbol to show to denote the set of all lambda double almost statistical convergence sequences weighted G. In here, if I take G and M, actually is the subscribe, G and M equal to the subscribe also this M, alpha between the 0 and the 1, we can get the notion of the lambda double almost statistical convergence of order alpha. And also here, if I take lambda nm equal to the nm and alpha equal to the 1, we have the notion of the double almost statistical convergence, which was defined, and here you can look at the reference level. And we will use this symbol, C hat, to denote the set of the all double almost statistical convergence sequences. So we define two theorems, actually the one theorem, but there is two, here, and G belongs to the G, and there is two double sequences, and the first one, if this limited x is equal to the x0, so this C is the complex number, also this limit is the value. And this next one, if this limited x is equal to the x0, and this limit is x is and equal to the y0, then this summation limited x to x0 plus y0. So next definition also, there is the lambda equal to the lambda nm. We mentioned it before, and G belongs to the G. T is the positive real number. There is the double sequence is said to be clear. This we had lambda double almost summable of the weighted G. If there is a complex number as such that this limited x is and equal to the 0, uniformly in P and Q. Usually we are using this symbol to denote the set of the all strongly we had lambda double almost statistical sequences of weighted G. Also, in this definition, if we take the GNM equal to the NM alpha between the here, this notation coincides with the notion of the strong lambda hat, we had the lambda double almost statistical, double almost summable of order alpha. So next, I have some interesting theorem here, and the theorem 3.6. There is the weighted G such that there is a m greater than 0 and the Rs and the n times n such that this is the G1 lambda nm over the G2 lambda nm less than m for all n greater than R and the the greater than S. That time this is the subset of this set subset of the set. If you get to the G equal to the capital G, the such that there is a m greater than 0, this is the such that this is the less than n equal to the m for all, n equal to the R, m is greater than equal to S. That time this is this set subset of this one. And the next one, C hat subset of the C lambda G hat, if this limit x is and equal to the actually is the limit x and greater than 0. Next theorem, if there is the two weighted G such that there is a m greater than 0, and this pair is belongs to the lambda times the lambda such that this is the over the this done less than m for all and equal to the greater than equal to R and also m the greater than equal to S. That time this is a subset of this set. And also there is the one corollary about this theorem 3.8. And another theorem, T is the real numbers, and U is also the real numbers between the 0 and the infinitive, and G belongs to the G. That time, this is subset of this one. So the basic theorem here, and there is the two weighted G1 and the G2, and they has the same condition here, looks like, and G1 over the G2 less than of the M for all, and greater than or equal to R, M greater than or equal to S, P from the here. So there is the actually main purpose. Double sequences strongly, we had the lambda almost double summable of the weighted G1 to L. Then it is the lambda almost double statistical convergence to weighted G2 to L. That means that this is the subset of this one. So from this theorem 3.12, it is possible to get the following corollaries, that corollary 3.13. And this part, the next part in this, of this talk, I will just define the Nif sequence spaces by using the Dolus function, and I will try to get into some inclusion theorems and also relations between the sequence spaces and the statistical and the lambda statistical convergence sequence of weighted G. So I defined the one Nif sequence spaces by using the Dolus function. So I have to give the Dolus function, what is this? I have to give the definition. Dolus function is going to the R plus to the R plus is the continuous, convex, and the non-decreasing function such that M0 equal to 0 and the Mx greater than 0 for positive x, and also Mx goes to infinity when x going to the infinity. These Dolus functions many people use to define the some Dolus sequence spaces. First, the Prussia and the Chowdhury, they used this one for the summability theory, and also I used some papers. They created the sequence spaces. So next definition, we defined here in the new sequence spaces by using the Dolus function. M is the Dolus function, and T equal to TKL, the sequence of statistical positive real numbers. G belongs to the capital G. So we define these sequence spaces. I hear the mistakes issued for the M here. So this limited axis and equal to the 0 for some L. If X belongs to the here, there is the mistake here issued for the M. We say that X is the stronger double lambda almost summable of the weighted G with respect to the Dolus function M. By particular case, it's possible to get. For example, if we here Mx equal to the X, lambda Nm equal to the Nm, TKL equal to the 1, so this sequence spaces reduced to this sequence spaces. If I take TKL equal to the 1 for all TL, so this sequence spaces reduced to the sequence spaces, and the TKL equal to the 1 and the lambda Nm equal to the Nm, so this sequence space is reduced to the sequence spaces. If lambda Nm equal to the Nm, so this sequence spaces reduced to the sequence spaces. So there is two theorem I will just mention without the proof. Theorem 3.15 and theorem 3.16. There are two weighted G, and there is the R greater than the 0, and there is the two the U0 and the B0 that belongs to the n times the n, such that G1 over the G2 less than R for all U greater than the U0, and the V of the V equal to the greater than the V0, and let M is the Dolus function. So this sequence spaces subset of this sequence spaces. And the next theorem, we are getting inverse inclusion. Just we are changing the conditions, and here also there is the 2 weighted G, and there is a positive R. There is the condition here, this one, and M is the Orus function. So, but it should be here, this double sequences is bounded. If it's bounded, so we are getting this inverse part of this inclusion. So we are getting, this is a subset of the this one. Actually, we investigate here what is the relation between the double almost lambda statistical convergence of the G and also the V lambda and the T between the sequence spaces. We investigate some relations. There is some references here. This references 9 is very important. The main study of the statistical convergence, and also Connor paper is this paper is very interesting paper, the statistical and the strong pieces of convergence of sequences. And there are some other papers for the double lambda statistical convergence or the double statistical convergence. 22 is this is the very interesting paper for the statistical convergence of the double sequences, and I think there is another paper, Salat paper. I already mentioned that this is the important paper because it proved that very interesting result here. And also I have some papers here. I think that's all. I would like to thank all of you for your attention.
Thank you very much, Professor Ekrem Savaş. Is there any questions? Is there any question? Any comment? Thank you, Professor Savaş.
Okay, thank you very much. Have a good night. I wish you all of you a very good, very pleasant weekend.
Thank you.
Okay, bye-bye.
Bye-bye. Oh, no.